Hey guys, it's Professor Musso again on EBB, Educational Building Broadcast. And today it's going to be 3D. Last time we spoke about systems, and today we will be speaking about structural systems, being one of the three major parts of a building, one being structural systems, second the skin, which is also some sort of system, and third being the finishes. Structural systems are about creating surfaces, like the surface of this table. It needs a structural system. Like the surface of the floor, it needs a structural system. So here's a chair I designed a couple of years ago, and it has a horizontal structure made out of wood, massive wood plate, and a vertical supporting structure out of steel columns. And the objective is to create a surface that I can sit on. If I have, for example, two walls, and I want to span from one wall to the other, I will use an element to form a surface. And you can remember that for a plane element like this one, it's about 1/35 of the span that I have to calculate for the height in a real building. So what I could do now is to turn it around. And you will see that if I turn it around, it will bend less than when it's not turned around. It won't bend at all. So where does that come from? So to show you the same effect, I can take this leaf here. The leaf is my surface. The surface spans from one side to the other, and you will see it bend in the middle. Now I'm giving it more height by folding it, and we will see that it will stay much more stable than the initial design. Much more stable. I can put my hand on it. So this is not a sponge as you might think, it's a model of a beam. And if I apply a load on it, you will see that the upper part gets shorter and the lower part gets a little longer. Yeah? If I take another beam like this one and I put a load on it, it will break from the bottom up, because in the lower part it gets longer and in the upper part it gets shorter. So we have compression in the upper part and tension in the lower part. And in the middle of the profile, there's going to be a neutral zone where we don't have neither compression nor tension. So let me draw this up for you. If I have a section which is horizontal and I have the neutral zone in the middle, I can divide it up into little squares. And I have a horizontal section and I have a vertical section. So in the horizontal section I have the surface and the lever arm, which expresses the distance of the surface from the neutral zone in the middle of the section. So here the lever arm always is the same, about half the square that I have been designing. So this is 6 times half of the square, which means 3 in total. And here in this case I have 4 times half of the square, and then I have 1.5 of the square and 2.5 of the square, and the same to the lower part of the section. So if I add up these lever arms, the sum is much bigger than the sum of these little lever arms here all together. And this is why a section that I put in a position which is far away from the neutral zone in the middle is much more efficient than if it's closer. But the disadvantage is that this here is much higher than the other one, so I need more space on the interior of my building. So you remember we wanted to create a surface. Then I can add another surface, and I don't need the joint in the middle, so they can be together. And if the span that I can reach this way is not big enough, I can put them on beams and thus create a bigger free span surface than would be the case otherwise. And these beams have to be supported in one way or the other. This could be by columns or by walls. And I could put a column here below, or it could be a wall as well. And if I have several beams, I could put them on another beam. So, and then this would be called the primary structure, and this would be called the secondary structure. And this would be the element that creates the surface. So in which way I dispose primary and secondary structure is going to have an influence on the dimension of the load-bearing elements. If I have 4 columns here in the corner of this rectangle, and I'm saying this is my primary beam, going from one column to the other, and the secondary beams are in the other direction, then you will see that the secondary beams have a larger span than the primary beam, and the primary beam gets half of the load. Here the secondary beam gets 1/4 of the load. So the smaller span will make that the primary beam and the secondary beam will be more alike in their dimension. So if I switch this around and I say, well, this is the primary beam and the secondary beam is in the other direction, then you will see that the span here of the secondary beam now corresponds to the primary beam in the first example. But it will get only 1/6 of the load, while this one here gets half of the load as before, and its span is much wider, so it's supposed to be much higher. So if I draw a section here, this will be rather high, secondary beam will be not so high, and here the primary beam and the secondary beams will be more or less the same.
Und los.